Okay, so now we open the second. Okay, so now we go to the second lecture. I think today we finish like half of them, not all, okay. So we can continue the rest of them in the next week, okay. So now we go to the second, the lecture A-2, the design count drive actuator through Kronos, our MUMPS process, okay. So now we consider the count drive actuator into a simpler model. So we now consider only two plates, okay. Remember, we have finger structures. The count drive, two finger structures stick to each other with some overlap. So we take out only the overlap area to consider. So the overlap layer actually is considered two plates, okay, two plates with some kind of overlap. We call the X, the overlap length we call the X, and with some kind of distance we call the Z, okay, and then the actuator have the width of the W, okay, and we have one set of actuators stick onto the wall, so we call it stator. Stator means that it's not a move. The structure is not a move. It's not moving. The other one we call the actuator. So the actuator is move back and forth, but the stator will stay there steadily. So like a electrostatic motor. So in electrostatic motor, we also have a stator. Stator stay over there, no movement. Only the rotor doing the actuation. So here we have a linear actuation, okay? So it's back and forth actuation. So we call this a moving structure called actuator, okay? So now, because we are using electrostatic force to drive it, when you have this kind of two plates put in together, and then they will form a capacitor between them. So if you apply potential among these two plates, there will be charge, okay, separate from the bottom to the top plate. So there will be an energy stored inside the system. So now we consider the energy stored in the system. Then we, after the derivative of the whole energy equation, we can get the force, okay, later on, okay. So now we consider the fundamental things. To provide charge onto this plate, these two plates first need to be conductive, okay? And then we need to connect these two plates onto a battery, okay? Or some kind of the potential provider, okay, to provide the potential. So now we consider there's a battery here, okay? The battery, inside the battery, we originally have a charge in total, we call it capital Q. There's a total charge inside the battery. And the potential on the battery is capital V, okay? So the total energy stored inside the battery, we call the capital U, is a V times Q, okay? So it's total energy in the battery. Now we consider to connect the battery into the capacitor. The capacitor is forming by these two plates, the count drive two plate, okay? So when you apply the potential along these two plates to surface, now we can transfer a small part of charge from the battery onto the capacitor. So the amount of the charge we call the small q here, okay? So the capital Q is the original charge. So the battery spare a little bit Q onto the capacitor, okay? You push the charge onto the plate of the capacitor. So now after this action, what kind of energy state will have? So we call the second state of the energy, we call the UC2. Okay, the current is the original one is UC1. The battery originally we have a battery contain the total energy. Now we spare some portion of the charge onto the capacitor. Now the energy will be stored not only in the battery but also in the capacitor. So the total energy will be the summation of these two energy together, one from battery, one from capacitor. Okay. So from the battery, now we have the total energy for the battery is a V times capital Q minus small q, because we deduct some small amount of charge onto the capacitor. So we lose some part of the charge. So the final one will be this one for the battery. But on the other hand, when we consider the energy stored inside the capacitor, we need to consider every time when you push one charge onto the capacitor, you need to resist some kind of force, right? For the first charge is okay because there is no resistance force. But when you want to push the second charge onto the capacitor, the first charge will have some resistance force to the second charge. So as the third one, fourth one. So this process is a continuous process. So we need to tackle the integration. So every time you put a small amount of charge onto this capacitor, you need to integrate the total amount of energy you put in. The small amount of energy every time you push one charge onto the capacitor will be V times dq. Okay. So you need to integrate over from 0 Q up to the small q, this total amount. Because Q equal to your capacitance times your voltage, Q equal to CV, okay? And your capacitance is actually is a constant actually. So you put the Q equal to CV into the equation, so C can be taken out because it's a constant, but you have a V over here. So after integration, you got a half CV square here. And the CV square here, you need to apply 0 of the Q, okay? And that means your voltage finally will become V. The final voltage here will be the same as your battery. So it becomes the final result plus 1/2 CV square. So now you have the total energy here for the battery and the capacitor energy here. And you add them together, you end out the final energy will be VQ minus 1/2 CV square. So compared to the original total energy inside the battery, you lose something, right? You lose a 1/2 CV square. So the 1/2 CV square is coming from the system energy reduction because of the you want to push the charge through the whole circuit into another part. So the resistance, including the circuits and also the capacitor resistance, will take out some energy into heat. Take out some energy into heat. So you got some loss here. Okay. So after you charge the capacitor, the final energy stays like this. Okay. So this is a fundamental, okay, of the energy status. But for our purpose, we want to use this as an actuator. So after the development of the energy state is not enough. What we want is the force, because the actuator, by using the actuator, we want to use the force of the actuator, not only the energy. So now we will consider how to extract the information from the energy equation into the force. Okay. So you want to do this, we need to consider different operation mode. Okay. So actually, there are several different operation modes we will talk about later on. So now we will consider this is two places ideal capacitor. For ideal capacitor, actually, for example, you have a two plates here, and the two plates give the width and the length is W times L. So the total area of the capacitor will be W dot X. Okay, X means the overlap, W means the width. Okay, and we we assume there's no fringe effect on the sides. So all the electrostatic, the electrical field will go through the center part of the plate. So now the capacitor of this two plate can be written like this. So the capacitor, the amount of capacitor is proportional to the area and inversely proportional to the distance. That means if you have a large area, you got a very large capacitance. And you have a smaller gap. You have a smaller gap between them. You got also large capacitance. Okay, so that's one thing. So this part is depending on the geometry of the capacitor you design. Large surface area, smaller gap, you got a high capacitance according to the geometry design. So in addition to geometry design, other things also govern the amount of the size of your capacitor. That is the material inside the space between two plates. Okay. So if you put like air, put it into vacuum or put it into water, so the material inside this region is when they are different, you can have different charge occupied on two different plates. So so these phenomena. So we use a very special parameter we call the dielectric constant to represent. So for higher dielectric constant, you have a higher K. That means under the same capacitance geometry condition, you can have more charge between two plates. Okay, for example, like a vacuum, the dielectric constant equal to 1. For air, it's a little bit larger than 1, but similar to 1. So for either in vacuum or in air, you can have a similar numbers of charge on the sides when you apply some kind of potential. But if you apply different material, like for Pyrex material, you can definitely increase the dielectric constant from 1 into 5.6. So under the same voltage, you can have 5 times, even 6 times more charges on the plates. Okay, if you apply different material, for example, Pyrex. For Teflon 2.1, for water it's pretty high, 80. Okay, it's much larger than most of the dielectric material you can imagine. So that's why when you buy the capacitor from the market, the most common capacitor is like you take it out from inside. You can see a piece of paper, right? Has been rolled inside the container, and there are some kind of solution accompanied with the piece of paper. Yeah. So originally, if you want to have a high capacitance, usually you can use water solution as your capacitor material inside between the two plates. Okay. And the absolute zero called the permittivity. Okay, it's a fixed number here. Okay. So this is a basic equation for the capacitance. So we can plug the capacitance back into the energy equation here. Okay, we get the final, total equation if we combine it together. Okay, now we can consider the operation at two different kind of mode. The first we call the constant charge mode. The meaning for constant charge mode means we operate the capacitor. After we charge the capacitor, we take out the battery and leave only the small charge, number of charge on the capacitor, and using this to do the actuation. This is the first condition, first type of operation. If you are doing this, and now we consider the total equation. If we plug into the C here, the UC, the final, actually take out the battery, so the battery energy won't be counted into the final system. The final system have the energy only of the small q on the capacitor its own. So when we apply the equation here, so UC, the final, the energy will be CV0 squared. V0 means the final voltage you apply onto this capacitor. The capacitor will have a voltage over here. So the voltage coming from V equal to C, Q equal to CV. So V equal to Q over C. So you plug, because we are operating in the constant charge mode. So in this case, when we change the gap, change the overlap distance, the voltage will be changed. However, the number of charge will not be changed, right? Because the charge has been isolated from outside. It won't leak out, won't go away. So no matter how you move, the charge will keep the same numbers. However, when you change the distance, if the charge keeps the same number, your voltage will be changed. Okay? So now we put the original voltage here, so then transfer into the original charge, because the charge will not be changed, but the voltage will change. So we're using the charge as a parameter here to see the total energy. So the total energy will be Q02 square over 2C. And you plug into C here, you got a final result here. Okay, now you can see the surface area of the capacitor is on the bottom, and the gap is on the top. So now we consider we move the plate in two different cases. The first one, we fix the gap, fix the Z, and move in X direction. We fix the Z, and then move in X direction. So Z become constant. Now X become a variable. So in this case, the force, if you move this direction, so you fix the Z, but you move in this direction. But now it's a constant charge mode. So when you move doing this kind of movement, you will find out your final force will be derivative of your potential, your energy with the direction of your movement, run U run X. So run U run X, you find out the force will become inversely proportional to the X squared. So the force is a nonlinear force actually. When you move along the edge, the force will become large because the overlap. You consider X on the bottom. So when the overlap becomes smaller, the force becomes large. Now leave this change from your thinking. So remember, it's constant charge mode. When you move the plate, the overlap a little smaller, then that means the charge density will be higher. Okay, when you have a large overlap, the charge will evenly distributed along the surface, right? But when you move along the edge to reduce the overlap, all the charge will push into the overlap region, from the large edge into the smaller region. So the charge density becomes higher. So you got a higher force. Remember? Is it understand? Okay? So this is the first mode you operate at it's constant charge and the fixed Z. Okay? This is the first condition. Now in the second condition, we fix the overlap. When we fix the overlap, actually the charge density is the same. But now we move the Z distance. This is the second operation mode. Okay? When you do the second operation mode, you need to take the derivative from the energy to the Z direction. Okay? Remember, in the equation, the Z is on the top. So when you take a derivative, the Z will be totally taken away. Okay? And now you fix the overlap. The width is over fixed. So the surface area is totally fixed. So now you find, if you fix the X overlap and moving in the Z direction, the force is a constant. Okay, because your charge density is the same, right? So electrostatic fields is going through these plates. The density does not change with your movement in a Z direction. So the force is always constant because the charge density is the same. Okay? So it's interesting. So in a constant charge mode, you move in Z direction, you got a constant force. Okay, sounds ideal. However, people don't use this as a common mode to operate. Why? Because when you take out the battery, leave the system inside the atmosphere. The atmosphere is not as clean as you think. In atmosphere, we have a lot of moisture, water molecule, and a lot of ions in the water molecule. So those water molecules are conductive. So your charge originally on the capacitor will be easily leak out through the electrodes when they contact with the air. So the charge won't stay there for a long time. That's a problem. At a very short time, all the charge will be leak out into the atmosphere. 漏在空气里面了，空气里面有湿气，湿气会导电，所以这些电容呢，很快就会失掉它的电荷。Okay, so that's a reason. So it sounds ideal if we using this operation mode, we can have a constant force along this direction, but it's not easy to use because the charge always leak out easily. So these are people in the past 20 years try to think of special material which can keep the charge always constant inside the material without leak out. But not easy. Currently, I think a Teflon might be the best material to keep the charge. But still, after like a couple months, even at most 1 year, you will leak out all the charge easily. Okay. Yeah, and other people try to use this to produce a microphone, condenser microphone. Not condenser microphone, different kind of microphone. So, yeah, it's a problem. Okay, let me finish this one before we take a rest. Okay, so now we consider the second mode because the charge can be leaked out. So what can we do now? So we can consider the second operation mode. We call the constant voltage mode. For the constant voltage mode, you won't take out the battery. You hook up the battery always with your capacitor. Okay? So when you leak out some charge, always some charges can be compensated from the battery into the capacitor. You won't leak out too many, actually, too much. You always keep a lot of charges here, no problem. Okay, so this is a second mode called the constant voltage mode. This most used common mode currently we apply. Okay, we call constant voltage mode. So now we consider the constant voltage mode. Your energy will not only the energy of the capacitor is on. In a system, we also need to combine the battery's energy with the capacitor energy together to take into consideration. So now the total voltage here include the battery and the capacitor is like the equation here. We have developed this equation before. Okay. So then we plug into the capacitor into the equation. So the final equation looks like here. So now we consider two operation modes as before. The first one, we fix the gap. We fix the z, moving x direction. So remember now it's a VQ minus C, 1/2 of CV squared. Now we are not replacing the V with the charge here, because the voltage here has been supplied by the battery here. So the battery here is always a constant. Okay, so that's why we leave the voltage here. We don't change that into the charge, the small q. Okay, in this operation mode, the voltage is constant. Okay, VQ is constant. Okay, now we take a derivative of the x direction. So remember, now the x is on the top, rather than on the bottom. On the bottom, we have a gap. Okay. So when we take a derivative along x, we keep the z constant. So now we got the final result equation here is a constant, actually. You got the V0 is constant, the width constant, the gap is constant. You keep the gap constant and then move in x direction. All other things are constant. So now you got a constant force. Okay. So if you apply the voltage onto the capacitor and then move the capacitor in the x direction, you keep the distance the same, the z the same. Interestingly, you've got a constant force here. Okay? Because when you do this kind of movement, you keep the same voltage. You never change the voltage. Okay? So that's why you got a constant force always, because your voltage is always constant. But if you change the distance, that's a different story. Okay. So now if you keep a fixed x direction but moving in z direction, now we need to take a derivative of this equation to z. And you fix the x position and do the gap closing. You find out the force is a nonlinear force. It's inversely proportional to the z squared. So as you have a closer, smaller gap, you got a higher force. And the force is a square root, is a square of the distance. So that means if you push it closer, you got a much higher. It's a parabolic profile. It's not linear profile. Linear relationship is a parabolic relationship. Okay, you got a much higher force. So that's why in the condrive actuator, actually we like to apply the constant voltage mode. Usually is a fixed z gap and move in the x direction. That's a common mode we apply usually, but sometimes we will apply the gap closing mode. We will talk about gap closing mode later on, maybe in next week. But this week we will focus on the laterally driven. We call laterally driven. That means that we move in the x direction, but keep the z distance, the gap, constant. Okay, let's take a rest. Yeah.